Hi, good evening all of you. I am Dr. Y. Chakrapani, Faculty, ESE Engineering Academy. This evening I am here to give the preparation strategy as well as important concepts in the subject computer organization. We know very well the computer organization is added in the GATE syllabus very recently. So soon it is going to gain its importance. More and more questions will come from computer organization in the GATE exam. In engineering service examination, already many questions are coming based on this particular subject. So let me throw light on what should be the strategy to prepare this particular subject, as well what are the important concepts we need to focus on it. So this subject, if you are thorough, any questions on CO as well as microprocessors, we can answer it very easily. So let me go through the details here. If you look at this syllabus, for electronics and communication engineering students in the GATE exam, so these are the 4 topics given: machine instructions and addressing mode, ALU and data path, control unit and instruction pipelining. So these are the 4 important topics. But to gain insight into these topics as well as into this subject, I'm going to cover usually, these are all the topics we are going to cover. It starts from computer arithmetic and ends with instruction pipelining. So we have to know all these things so that we can answer to the questions in the exam in an effective manner. If you look at the syllabus for engineering service examination, okay, so it is going to be same as this one. So it is going to have extra the memory organization, peripheral devices and trends, as well hardware and software issues. So these are the additional topics we are going to have for engineering services. That is nothing but memory organization, IO organization, and then these are the hardware and software issues. Looking at the syllabus for ESE exam for EEE students, it is going to have same thing like computer architecture, CPU, memory organization and IO organization, and then peripheral devices. That means here that topic hardware and software trends, that is not there in this one. Again, for ESE students, whether it is ECE or electrical students, to answer to the questions in the engineering service examination, these are the 9 topics we need to cover. So you can see them, they are same as that of GATE syllabus except 2 additional things. One of them is the memory organization and other one is IO systems. So apart from the entire GATE syllabus, these are the 2 things we need to focus. Of course, in this memory organization, we are going to see what is the cache memory, how it is organized, and what are the different types of mapping techniques. And similarly, here in input-output systems, how you are going to connect input devices, output devices to the CPU. That is, we are going to learn it. So this is for engineering services examination. Fine. As far as weightage, if you see, definitely as of now, it is less in the GATE exam for both ECE and EEE students, and it is more in engineering service examination. But we are expecting that the weightage for computer organization will increase in coming years. So if you see in the CO, the marks so far asked have been, in 2021 it's asked for 2 marks, and 2022 it has asked been 3 marks. Similarly, if you go for engineering service examination for ECE students, then these are the marks starting from 2019. These are the number of questions, okay? These are number of questions, okay? So 13 questions have come from CO. 15, 2021, 11 questions, 2023, 14. Means consistently 10 questions are coming from computer organization for ECE students. Similar fashion, what is the weightage for CO subject in the GATE exam for EEE? Even though it is not mentioned completely, sometimes the question will come from CO. Look, so in 21, 1 mark has come for EEE students, and in 2022, 2 marks question has come. Okay. Then what about engineering services for EEE students? This is the distribution. Starting from 2018 to 2022, the number of questions that appeared are like this: 12, 13, 11, 9, 13. Of course, these questions do include another topic, that is computer fundamentals. So computer organization, computer fundamentals together, it is going to have this many number of questions. Okay, so now I have given how the questions are coming on this subject in GATE exam as well as your engineering service examination. Let us move forward. So for this subject, vast number of books are available, but reading them is time consuming and it requires lot of patience. So to make it very simple, these are the 3 books I suggest for the student to go through if at all he finds the time. One is none other than Maurice Mano with the title Computer System Architecture. He is well known for digital, and he has also written the book on computer architectures and organization. So this is one of the very good book here. Coming to the second one, Computer Organization and Architecture by William Stallings. So his explanation is also very good, and it is going to be very descriptive. So you have to study with a little bit of patience. And third one is Computer Organization by Carl Hamachar. So this is also very good book, especially for pipelining. So these 3 books are enough to go through for both GATE exam as well for engineering services examination. Fine. So if you want to succeed in the GATE and ESE exam in this subject, what you need to do? See, every subject will have different type of strategy. That's the reason I'm here to tell for CO subject what should be the preparation strategy. Okay, fine. First one is you should understand what are the needs of the competitive examination regarding this particular subject. So how he is focusing, on which topics he is focusing, is he covering the entire syllabus of CO, or is he focusing on the restricted areas? So that is what you need to observe it. For that, you have to look into the previous year question papers, and from that you should understand what is the main focus. For example, most of the times the questions come from floating point numbers, instruction pipelining, control unit. So like that, there are some predominant topics are there. You have to make it out, and in that particular topics you have to prepare. So my suggestion is you have to focus mostly on this floating point numbers, Booth's algorithm, control unit, and then instruction pipelining. Okay? Right, let's go ahead with that. Second thing is explore the syllabus. That means once you understand which topics are important, then your duty is, okay, what is the syllabus in that particular aspect? For example, if instruction pipelining is there, what are the things I need to study? What are the things I need to avoid it? See, arithmetic pipelining is not given, so don't read it. That much is not required. So he has clearly mentioned it is instruction pipelining. So restrict your preparation only to the required topics without wasting your time. So if you start reading about parallel processing, what is the meaning of pipelining concepts, what is the meaning of superscalar architecture, what is the meaning of arithmetic pipelining, it is going to take a lot of time. You will gain the knowledge, no doubt about it. But the thing is, can you justify the your time for important topic preparation? That is very crucial. So that's the reason I have written clearly, explore the syllabus and try to focus only on the syllabus. That's it. For example, control unit is there. In microprogrammed control unit, there is vast explanation is there. That is not necessary for us because your target is now to succeed in the competitive examination. So that's the reason you have to learn it in a very simple manner, such that any problem comes in the exam, you must be able to answer. Any conceptual question comes in the exam, you must be able to answer. So that comes by practice. If you see 2 to 3 times the syllabus and then what is the subtopics in that syllabus, you will definitely understand which one to provide importance, which one to avoid it. Next one is organize the subjects. Of course, I am telling in general. So keep the CO at appropriate place. My suggestion is, once the digital part is over in your preparation, then only you have to come to CO. Because most of the topics in CO, it requires the concept of your digital electronics. Whether it is signed number multiplication, the booths multiplication, or if you want to go for arithmetic logic unit designing, or you want to go for any other calculations, we require the concept of digital electronics. So without knowing digital electronics, probably this subject is not going to be understood completely. So suggestion is, prepare digital first. Once you complete that, then you can come to this particular computer organization. So organize the subjects in that manner such that by the time you come to CO, its fundamentals should be completed. Of course, plan the timetable. That's what I said, no? You categorize all the subjects into very, very important subjects, okay, moderate important subjects, and then easy subjects, like that. So you can keep CO also at one level in that fashion and then try to prepare it. Important thing now is practice problem solving. See, most of the times we give the solutions for the problem, you feel that you understood the entire concepts, and also you are very confident of answering the questions. But that's not true. Reason is, as long as solution has been provided, you will easily understand it, but you cannot redo the things. So that's the reason my suggestion is, take the questions from the previous papers, GATE as well as engineering service examination, and try to solve on your own. So that is going to evaluate your performance. It will tell most of the things. How is your preparation? Are you at that level of acquiring the good rank or not? Does it require any improvement? In which topic you are lacking and in which topic you are strengthy? Everything will be known only if you solve the problems. Try to do that. Of course, along with problem solving, that's not enough, because you have to do the test. Okay, so you have to appear for test series. There you are going to get your exam-like environment. So in that exam-like environment, you try to answer to the question. So there the time is restricted, you are in an exam hall and you have to answer many questions. So that you need to practice it. So problem solving first, then once you gain the advantage in that one, then you can go to the taking up the tests. And importantly, you have to be motivated till the end. Okay, so don't decline your motivation level. So you have to keep up that performance. At times it may come down. Sometimes on few days you may not feel you are very confident of getting the rank, but don't worry about it. The very next day, start a fresh day. So keep up that motivation until you appear for GATE as well as ESE exam. Suppose in one of the test series you got less marks, don't mind it. Okay, so next one you try to focus more on that and try to get more marks. So one exam is not going to evaluate your skills. Okay, that's the reason. Don't worry if you get less marks in one of the topic and one of the subject and one of the exam, right? So these are the 7 points you need to remember if you want to succeed in GATE exam as well as engineering services examination, right? Well, you know that in the computer organization, if it is GATE exam, we are going to get mostly the multiple choice questions, multiple select questions, and numerical answer questions. So this is mostly problem oriented, which you know already. But when it comes to engineering service examination, the questions are going to be, apart from these three, you are going to have match the following. Okay, so list 1 is given, list 2 is given, we have to match them. So that requires little bit of fundamental knowledge. And also in engineering service examination, one more type of question will come, statement 1 and statement 2 questions. So those type of questions also you need to practice it. Okay, so if you do that, then you can easily answer the questions in the examination, right? Let me give a brief idea about what is computer architecture and computer organization. You know that this is instruction set architecture. ISE stands for instruction set architecture. and this is going to be called as computer architecture. You can see it is the interface between the compiler as well as the hardware. The bottom part is called hardware, the top part is called as software. So in between software and hardware, I'm going to have this instruction set architecture, which is called computer architecture. So the duty of this is it has to fulfill the requirements of compiler. At the same time, it has to see that the hardware is simple. So it requires a lot of optimization. Okay, it requires a lot of optimization. And then the bottom part of this one, which is called as hardware, this is called as computer organization. So this is computer architecture and this one is computer organization. So what does this computer organization consist of is starting from CPU, memory, I/O systems. So all put together we are going to call computer organization. So this is the what you call level of abstraction of a computer. The top portion contains software, the bottom portion contains hardware. In between software and hardware, I have computer architecture. That is called as instruction set architecture. Yes. Now let us look at what's the definition of computer architecture. Okay. So it is going to deal with the total functional behavior and logical aspects of system implementation. Number 2, it is going to be interface between the machine and the software. That means it is the interface between hardware and the software. So this instruction set or computer architecture will contain instruction set architecture, which is going to having instruction format, instruction set and addressing modes. That's it. What is computer organization then? I told you it's purely hardware. Look at the definition of this computer organization. What it is going to tell? It is the hardware components and the interconnections among them that is going to implement architectural specifications. So whichever hardware I'm using and the connections among them I'm using to meet specifications of the architecture is called as computer organization. So the main focus of computer organization is it has to improve the system performance. So let me tell one example. Suppose if it tells that it requires one adder, which type of adder we have to use, that will be decided in such a manner that adder has to improve the system performance. Okay, that is the, you may use parallel adder, you may use carry look ahead adder, or you may use carry and save adder, whatever it might be. So overall, the system performance, it has to improve. Fine. So the next thing, generally questions will come from this topic, floating point numbers. You know that compared to fixed point numbers, the floating point numbers are used in scientific computing. It is used in scientific computing. So whenever you want to write Avogadro's number, charge of an electron, mass of an atom, everything, we write it in the form of floating point numbers because it is having this advantage. Using the floating point numbers, we can increase the precision, which is also called accuracy, or we can increase the range of numbers represented. So that's the reason we prefer floating point numbers compared to the fixed point numbers. I think you would have known a digital signal processor, they will be available with fixed point as well as floating point. So digital signal processor with floating point is much costly compared to digital signal processor with fixed point one. So that's how the advantage. It increases the range, it increases the accuracy. That is the advantage with this. Okay, so in these floating point numbers, we are going to use two types of normalization. So why we go for normalization is to utilize the bits in mantissa in an efficient manner. Okay, so any particular floating point number, it is going to have it like this: sign, exponent, mantissa. So in this mantissa, whatever number of bits are there, to utilize them effectively, then we are going to use this normalization. Fine? So two types of normalizations will have. Some of the floating point numbers will follow explicit normalization, and some of the floating point numbers will follow implicit normalization. Okay? It depends. Then floating point numbers are of two types. One is conventional floating point numbers, other one is IEEE 754 floating point representation. Okay? So depending on the people adapted, it is going to have, this is the two types of representation. In conventional floating point representation, we can go for any type of normalization. We can use either implicit normalization or explicit normalization. But when it comes to IEEE 754, it is going to follow only implicit normalization. Fine? So that is what the difference between the two. Fine. So conventional floating point numbers are having little drawbacks. To overcome that, we go for IEEE 754 floating point representation. Right. So in this IEEE 754 floating point representation, we'll have single precision, we will have double precision. So I take only single precision, which is going to use 32 bits. So 1 plus 8 plus 23. First one for sign of the mantissa. Next one for biased exponent. Next one for mantissa. So that is going to be 1 plus 8 plus 23. And then the decimal value of any implicit normalized one is going to be calculated by using this. So if already floating point number is given, how to find its decimal value is you use this formula, where this one is called as hidden bit. Fine? So in this single precision floating point representation, what is the range of numbers you can represent? So the minimum value that can be represented is this, and maximum value is this. Yeah, look at this. This is the minimum value you can represent. 1 into 2 power minus 126. Maximum is this one. So beyond this, can you represent in terms of IEEE format? Yes. So these will be shown as special numbers. 0 is shown as special number, and also the value smaller than the minimum value. This is also shown as a special number called as denormalized number. Okay, right. Now let me show what is the table for this. The exponent from 1 to 254, I use it for normal floating point numbers. I think you might be knowing that. But whenever exponent is 255, whenever exponent is 0, then it is going to represent special numbers. So based on this, the objective questions will come. Okay, quickly let me complete. E255, mantissa is 0, it is infinite number. It can be plus infinity or it can be minus infinity. Next, E is 255, mantissa is not equal to 0, it is not a number. I have written at the bottom, what is the meaning of not a number? This one. Next, E0, mantissa is not equal to 0. This is called a denormalized number, which is going to be calculated by using this principle. Then E0, M is also equal to 0. It is going to represent plus 0 or minus 0 depending on the sign bit. So apart from the direct floating point number representation, it is going to represent the special numbers like this. Infinity number, not a number, denormalized number, plus 0 and minus 0. So many times objective questions will come based on these combinations. Okay, so sometimes question will come, represent 10 in IEEE 754 single precision format. I quickly show this. How do you do this one here? Right. So step number 1, write that given decimal value in binary form. Okay, let's go to the next one. Step 2. Go for implicit normalization. So this implicit normalization can be written as 1.010 into 2 power 3. That means the binary point, I'm moving it from here, which was originally here, I moved it to this place. So as it is coming towards left side by 3 bits, hence I have to write it as 2 power 3 quickly. And then this is going to be your mantissa. What do you call this? This is called hidden bit. And then this is called true exponent. Yeah. So step number 2, after implicit normalization, find out what is the hidden bit, what is the mantissa, and what is the true exponent. Now third one, you find out biased exponent. Biased exponent can be found out by adding the bias to this true exponent. So that is going to become true exponent is 3, bias is 127, which is equal to 130. Write this in terms of binary using 8 bits. (128) plus 2, that will become 130. So that is your biased exponent. Okay, so now you get into the IEEE format. Step 4. Sign of the mantissa 1 bit, exponent 8 bits, which I already found it. Mantissa 23 bits. So this mantissa, I should extend it to 23. So this is going to come in this fashion. Yeah, quickly. So this one is and then this is the mantissa. So this is the 32-bit number. Now you have to convert into hexadecimal. So this becomes 4, 2, 41200000 hexadecimal. So a decimal value of 10 in IEEE 754 single precision format will be shown with this value 41200000H. I think these are the standard steps you need to remember. Write this in binary form, go for implicit normalization, find out biased exponent, all this information, put it into this form. That's it. Okay. So sometimes the objective question comes like this one. So a single precision floating point representation of a real number as per IEEE 754 standard is as follows. This is sign, exponent, mantissa. Sign means it is sign of the mantissa. Then Which one of the following choices is correct with respect to the smallest normalized positive number represented using the standard? So he is asking about the denormalized number. For denormalized number, we know exponent should be 0 and mantissa should be not equal to 0. So in the table, when I am discussing, I have told it here, any denormalized number, exponent should be 0, mantissa not equal to 0. That is the right answer for this. So among the 4 options, which is the right one? You can see the B option is the correct one. Look at this. Exponent is here 0. And then the mantissa is not equal to 0. So this is the right answer. Just for your helping sake, I will tell you what are the other things going to indicate. Look at this. Exponent is 0, mantissa is also 0. What does it indicate? Either plus 0 or minus 0. Okay, first one, plus 0 or minus 0. Next, exponent is 1 and mantissa is all zeros. This is going to represent a floating point number. I told exponent should not be 0 and 255 for your floating point number. Similarly, this one. Exponent is 1, mantissa is all 1, so it is going to represent a normal floating point number only. So like that, you have to remember what is the decimal value of this. So for this question, the correct answer is B. Yes. So what is the Booth's algorithm? It is used for the signed 2's complement number multiplication. So many times the question will come based on this Booth's algorithm. Remember that it is meant for multiplication of signed 2's complement numbers. Okay, in this Booth's algorithm, the property is number of subtractions will be either equal to the number of additions or 1 more than the number of additions. Okay, so that means I can tell in Booth's algorithm, k is equal to either n or k is equal to n plus 1, where k is the number of subtractions, n is the number of additions. So I am highlighting which question may come in the form of the bits here. So this is the relation you are supposed to remember. Okay, so that is the nature of Booth's algorithm. Of course, that flowchart I have given here, what is to be done based on these values of qn and qn plus 1. So if it is 0, 0 or 1, 1, it will have only one step. But if it is 1, 0 or 0, 1, you have to perform 2 steps. So if it is 0, 1, we have to perform addition. If it is 1, 0, you have to perform subtraction. You can see this is nothing but subtraction. So like that, one step extra will have it whenever qn plus 1 value is 1, 0 and 0, 1. So this is the Booth's algorithm. Yeah, coming to the memory. We know that 2 types of memories we will come across. One is byte addressable memory and word addressable memory. Remember, byte stands for 8 bits, but word, it stands for 8, 16, 32 or 64 bits, etc. The word size is going to differ. It depends on the processor. So memory is going to be 2 types. You can access each byte, but sometimes you can access only one word. So first one is called byte addressable memory and second one is called word addressable memory. So sometimes the questions will come like this. There is a memory size given here 4096 into 16, meaning the word size is 16 here. In that case, how many number of bits are required to address each word? Okay, so if you want to get each word out, then how many number of bits we require? And if you want to get each byte outside, then how many number of bits we require? So I just solve one of them. You try to remember this. The first one is 4096 into 16. Okay. So whenever you write the memory size in this fashion, the 12 will tell that how many number of address lines are required and 16 will tell how many number of data lines required. Hence, it is going to require 12 address lines. Okay, so this requires 12 address lines and of course data lines are 16. But what about if it is byte addressable memory? For that what you have to do is, this one should be equal to 2 power x into 8. So value of x will tell how many number of address lines I require to access each byte. Okay, so this is 8 twos are. So this becomes 2 power 13 is equal to 2 power x. So x equal to 13. Fine. So in that manner, we have to quickly do this one here. Similarly, 512 into 64 can be written as 2 power 9 into 64. Hence, it requires 9 address lines. Similarly, for this, how many address lines it requires is this one. 512 into 64 is equal to 2 power x into 8. So this is word addressable memory, but in this, the byte addressable memory, you have to express it in this fashion. So if you calculate this, I'm going to get the answer, 88. This becomes 2 power 12 is equal to 2 power x. So like this, many times the questions will come based on the memory. So whether you are accessing each word or each byte, you have to observe it and tell how many number of address lines we require for each of them. Okay? Right. The instruction format. We know instruction contains only one opcode and then number of operands. So that is the combination of instruction. Opcode followed by operands. So in that, we are going to get many times this type of question. The length of the instruction in computer is 8 bits. And then the computer supports opcode expanding. If it is having 3 2-address instructions and 2 1-address instructions, find the number of 0-address instructions. Okay, so how to do this one is very simple. We can put it like this. So total number of instructions will come as 2 power 8 because it is a 8-address instruction. Okay, 8-bit instruction is equal to how many number of 2-address instructions are there? 3. That is 3 into, yes. Each address can take up 2 power 3 possibilities. So 3 2-address instructions. 3 into first address can take up 2 power 3 because it is having 8 registers. Sorry, first let me write number of bits required for each register. Is equal to 2 power n should be greater than or equal to 8, that is n equal to 3 bits. So the address field is 3-bit. Yes, so 2 power 3 into 2 power 3 plus Next, he told that there are two one address instructions. Two one address instructions, that is 2 into only one address. One address can take up how many possibilities? 2 power 3 plus the number of zero address instructions are n. So this is the total number of two address instructions, this is total number of one address instruction, and this is zero address instruction. From this you can calculate what are the total number of zero address instruction. That is, you can say that take 2 power 3 common, so 32 minus 26 is going to be 6. Yeah, that's it. So if you remember how to write this, any such question we can successfully answer to this. It's very simple one. Okay, right. So number of zero address instructions are totally 48. Yes. So we have different types of addressing mode. In this he is asking R1 value is 300, R2 value is 1200, and then the word length of the processor is 32. Size of the word is 32 bits. Okay. The effective address of the memory operand in decimal for the instruction store. Okay, this one. Always remember the store instruction store instruction, it is going to have the data transfer from register to memory. So there is no standard format which is source and which is destination here, but what you have to understand is wherever memory is there, that is the destination. So R5 is the source in this particular store instruction, and this one is the destination. So it is saying that R5 value should go to the memory which is given by this address. What is the effective address here? Effective address is nothing but R1 plus R2 plus 70. The values of R1 and R2, they have been given as 300 and 1200. Substitute into this. That is it. So the answer to this question is effective address is equal to 1570. That means, what is the meaning of effective address? It is the address of the operand. It is the address of the operand that is given by 1570. So this is as simple as this. Yeah. So sometimes in engineering service examination, he will give the match the following. So different addressing modes are given and different features are given. So you might not be knowing the answers for all the 4 of them, but if you properly match with a little bit of logic, we can easily understand. First, search for which one you know it. Okay, so we know very well this indexed addressing mode, it is used for array processing. Okay, so indexed addressing mode, we use it for array processing. So that means B should be equal to R. So the answer should be either first or second one. These two are wrong. Okay, elimination process. So 2 of them I can eliminate because I strongly know that indexed addressing mode is used for array processing. So the answer should be either A or B. Okay, then you have to go for this implied addressing mode. It is always operated on accumulator. Remember, so here I don't mention what is the operand, it is implied, and that implied operand will be accumulator. So for implied addressing mode accumulator, that means the D should be equal to Q. That's it. So two of them are established, then you can say that the answer the A is the correct answer. A is the correct answer for this. That is base addressing, I use it for position independent. This is also called program relocation. I know that base addressing mode, we are going to use it for program relocation, which is nothing but position independent. And then this one, stack addressing, it is called re-entrancy. So values will enter into the stack, exit from the stack. Enter into the stack, exit from the stack. That's why it is called re-entrancy. So finally, the correct answer is A. Okay. So like this, by elimination process, we can easily find out the answer to this. Of course, sometimes based on the CPU performance, questions will come, and how they are going to ask you is like this. I'll tell you one simple question here. We want to execute program A on two processors. I want to execute on processor 1, which is supplied by Intel, assume that. Same program A, I want to execute on processor number 2, which is given by AMD company. Okay, so which one is better? You can see that the free instruction count for this program in this processor is 10,000, but here the instruction count is 12,000. That means total number of instructions. And then he has given some details, how many number of instructions are there and how many cycles per instruction it is going to do it. So which one is better for this? He told that processor 1, it's having cycle time of 1 nanosecond only. That means the frequency is 1 by cycle time, which is equal to 1 gigahertz. Coming to here, the cycle time is 0.714. That means the frequency of this is, that is frequency of processor 2, it is greater than 1 gigahertz. Fine. So this is the frequency of the processor 1 and this is the frequency of processor 2. So can I say that the frequency of processor 2 is higher than the frequency of processor 1, hence it is better to execute program A on processor 2. Can I say it like that? No. So the frequency, instruction count, CPI values, it will not decide. What it decides the performance of any computer is execution time. So we know that execution time is given by this formula. So what I have to do is, for this program, what is the execution time on processor 1? Use this formula and calculate. For the same program on processor 2, what is the execution time? Then calculate using this formula. Then whichever processor is having smaller execution time, that is the best processor to execute this program. Okay, for that, what I have to do? First calculate CPI average and then substitute into this. I know IC value, I know the cycle time value, so only thing you have to calculate CPI average. For the first one, CPI average is 0.2 into 5 plus 0.4 into 2 plus 0.4 into 1.5. This is 1.5, yes. So like this, we are going to do it. Look at this. 0.2 into 5, 0.4 into 2, 0.4 into 1.5, it is 2.4. So then calculate the execution time. Next, same program is executed on processor number 2. Then again, calculate what is the cycles per instruction, CPI value. It came as 3.125. And then substitute into the formula, it is going to come this way. This is 26.775 microseconds. Sorry, 26.775 microseconds. So conclusion is, it is better to execute program A on processor 1 compared to processor 2. Processor 1 is taking 24 microseconds. Processor 2 is taking 26.775 microseconds. So that is how you have to compare the CPUs. Okay, so as usual, arithmetic logic unit. Based on that also very many questions will come. Reason is, it is related to digital also. So how do you construct a multiplier? How do you construct a subtractor? How do you construct an adder? Based on that, many questions will come. Followed by the data path will be given. He will ask you to calculate so many parameters based on the data path. What's the meaning of data path? It is functional units and their interconnections, where a functional unit is going to consist of ALU, buses and registers. So the combination of ALU, registers and buses will be called as data path. Yeah. So many times the questions will come like this. So this is the bus what he has given, and these are the general registers. So to this bus you can see all the registers are connected. S register, T register, R0 to Rn register, program counter, instruction register, memory address register, memory data register. Okay, this one. So he told that for memory read operation, it requires 2 clock cycles. So why it requires 2 clock cycles for memory reading is, 1 clock cycle is to write the PC value into MAR, and second value is to write from memory into MDR. You know that this is connected to memory. Here it's going to have a memory here. So PC value to write it into MAR, it takes 1 clock cycle, and then from the memory value should come to MDR, that is the second clock cycle. Okay, like this. Then he is asking for this how many number of clock cycles it requires. So it depends on what is the data path given here. If you want to add R0 and R1, can I take them directly to ALU? The answer is no. So first thing, R0 should be brought into S register, R1 should be brought into T register, and then the result of ALU, you have to write it back into R0. So for first one, the answer is 3 clock cycles. Okay, answer is 3 clock cycle, right? So it is going to be like this one. So the time is going to be in this fashion. R0 value should come to S register, that is 1 clock cycle. R1 should come to T register, second value, and then whatever result is coming here, that should come back into R0, that is the third clock cycle. You may ask me, sir, what about the time taken by ALU? The time taken by combinational circuit, we are not going to count it, okay? Because while calculating the clock period, the time taken by combinational circuit, it's already taken care. So don't count the time taken by ALU. That's it. So this is going to require 3 clock cycles. In the similar fashion, there is one instruction called call Rn, subroutine, and its operation is given by this. Then he is asking, what is the minimum number of cycles required in the execution cycle? Okay, minimum number of cycles required in the execution cycle. And you know that any instruction cycle is going to consist of 2 parts. One is called fetch cycle, other one is called execution cycle. So in this problem he is asking, in this execution cycle, how many clock cycles are required? Okay, and I told that the program counter is incremented in the fetch cycle itself. So the program counter is incremented in the fetch cycle itself. So don't count that time into execution cycle. Then how many clock cycles it requires? I think you can easily count here. For the program counter value, to write it in RN register, it requires 1 clock cycle. Next, the memory has to be read and written in PC. This requires totally 3 clock cycles. Why? Already has given the description. For any memory read operation, it requires 2 clock cycles. First one is the PC value, I should write it into MAR. It requires 1 clock cycle. What is the next one he has given? For loading the address in the MAR, and this next one for loading the data from the memory into the MDR. That means so for this memory itself, it takes 2 clock cycles. Then finally, from the memory, whatever value comes, that should be loaded into PC. So that is nothing but third one. That's it. So the answer to this question is 4 clock cycles. So for the first one, it requires 3 clock cycles. This is the answer to this. And for the second problem, it requires 4 clock cycles. Okay? Yes. So in the control unit, most of the times, the question will come based on the microprogrammed control unit. So he told one microprogrammed control unit, which is going to be shown like this. Fine. So he's telling that the width of the micro instruction is 26 bits. And he told the micro operation field, it is going to contain 13 bits. This is micro operation field. Next address field is X. And then the mux select field is Y. That means 13 plus X plus Y equal to 26. Okay, that's what it is. That is and next one. There are 8 status bits at the input of the mux. Remember, based on how many inputs mux is having, the mode bits are going to be selected. As mux is having 8 inputs, the mode must contain 3 bits. So that's it. So Y is calculated as 3 bits. So 13 plus X plus 3 equal to 26. That's it. So Y field is going to contain of 3 bits and X field is going to have 10 bits. And one more thing is asking, what is the size of the control memory? As it contains 10 address lines, okay, that's the reason size of control ROM is 2 power 10. So final answer is X equal to 10, Y is equal to 3, and then the final value is 1024. 10, 3, 1024, that is the right answer for this. So in this fashion, if you look at all the topics, the questions will be looking like very lengthy, but answers will come in a simple manner if you have the conceptual background. So like this, You go through what is the meaning of instruction pipelining and what are the corresponding problems. Similarly, memory organization and I/O systems. So once you go through such type of problem, if you gain the confidence on solving these things, you can easily score good number of marks in computer organization. So this is what the points I wanted to tell in this presentation. I wish you best of luck.